In this video, I want to look at what is the size of this green circle, the radius of this green circle. So I started off, I'll say, with a unit circle, the large one, and then it's known that I can put six circles around that sort of inner circumference, if you will, and that those are uh, one third of the size. That I could put one more of these circles in the middle of these. And so I put six circles around the unit circle, and that was a third in size. And then I took one of those and did the same, put six circles around it. And then that size, which would be a third of a third, which would be a ninth, uh, looked like it would fit in here. So I asked that question. Is that sort of a ninth of the original? And the answer is no. It's close to a ninth, but it's not a ninth. And my picture, sort of, there are little gaps here, which there aren't up here. So if my picture is accurate and it's just a sort of bad drawing in PowerPoint, so it could be a bad drawing, uh, but it's accurate enough to say that no, I needed this circle's a little bit bigger than a ninth. And then I asked, well, what is it? Okay. And I decided to tackle it because I've gotten these circles previously playing around with circle inversion on a honeycomb lattice. So I went back to that problem in Mathematica. So that's the problem. What's the size? What's the radius of this circle? Okay. So here I am in Wolfram Cloud, and here's the previous video I made and the PDF for it. And this brought up a different problem, which I have not solved, maybe a more practical problem. Um, if I copy this code, this from the PDF that I had previously saved, and paste it into, let me make a new notebook and paste that in and shift enter, it does not understand it. This came from Wolfram Cloud, saved as a PDF, and I took that PDF and pasted it back into Wolfram Cloud, and it's saying, I don't know what you're talking about. And then if I say open Notepad++ and paste, I see that I've got some like funny characters. And I can sort of recover this in a painstaking way by saying, oh, that first thing after graphics is a square bracket, and I can do find and replace all and replace this, copy this character, do a search, replace, paste that up there, Control V, and then again, what was that? That first thing was a square bracket. So replace it with an open square bracket and do a replace all. And I can keep playing this game. And you'll see there are slashes that it's missing. This is pi divided by 2. There are open curly brackets and closed curly brackets and closed square brackets. And some of the square brackets, it knows the sort of normal size, but then if it changes the size of them, it doesn't recognize them. But if anybody knows a way to sort of less tedious way to do that, that would be nice. Okay. Anyway, so back to this. Okay. So again, I'm looking for the radius of this circle. So I went back and re-entered this. So I have this honeycomb lattice, hexagons, honeycomb lattice with circles inscribed in them. And it is, I can do that. Here's my regular polygon under graphics. So I'm using the graphics in Wolfram Cloud. And this is that center hexagon. And so it's centered at 0, 0. And this is I'll call it the radius, the big radius, the radius to the farthest point. So in the hexagon to the sort of corner of the hexagons. And so that's 2 on the square root of 3. And then the short distance is a 1 in here because I was, again, working sort of with a unit circle. So the inscribed circles are unit circles, as we'll see here in a minute. There's the circle that's in their same center with a radius of 1. So in Wolfram's notation for the regular polygon, this is the sort of furthest distance, the farthest distance. So there are 6 sides, it's centered at 0, 0, and this is taking me to the corner. And then I added that, and then I added the circle, and then this is me looping around, getting the other hexagons and the other circles. Okay. So that's the game I played before, and I inverted those circles. But now I'm going to add to that what I'm interested in. Again, as you recall, I'm interested in this circle. Well, I want to find its inverse. So its inverse, I'm going to uh, invert that honeycomb lattice. And so this circle is touching 3 circles. And so I'm going to put circles here. And then those, when I do a circle inversion, they're going to be the circle I want. Okay, so here's all my code here. And I've added these little red circles. Okay, so that's these LC, the little circles. Okay, and they're the red ones. And where are they located? They're located at 2 divided by the square root of 3. That is that sort of big distance to the corner, and cosine and sine of pi I divided by 3. So I'm dividing my circle up into 60 degrees, going around 6 times for the 6 different angles. And so the first one, the 0th one, if you will, would be this horizontal. And that's the location of the centers of those circles. And then the radius of that circle is the difference between the distance from the center to the corner to the center to the circle. So the center to the corner of the hexagon was 2 divided by square root of 3, and the center to the distance to the circle, it was a unit circle, so that was -1. So that's the radius of those little circles. So that makes sense. Okay. Now I want to find the distance to the further end, because this center circle is going to be my circle of inversion. I want to invert the far end of that red circle. And so I want to find out how far it is from my origin. And we know that it is, if I take 1, that takes me to the edge of the circle. And then if I take 2 times that radius that we just talked about, that is this distance from the center to there. So I said 1, the radius of the circle, plus 2 times the radius of the little red circle. That'll take me to the far end of the red circle. And I called it far point, and I said simplified. So there it is. 4 divided by the square root of 3 minus 1. Okay. Now I want to do the circle inversion game. So where is that point inverted, if I do circle inversion, you take uh, the radii, you take, say, 2 points along a radius, and you want their product to be 1 if you're inverting around a unit circle, which I am. So I'm going to take that far point was along a radius, and I want to find its corresponding inverted circle. So that'll be, I'll call it CP, the close point. Um, and so I took 1 on far point. That's my circle inversion. And I did a full simplify. Simplify wasn't enough. It was giving me a very sort of crappy looking answer, but full simplify sort of did what I wanted it to do. So let me enter those. So that's where I got. So that's the far point on the edge of the red circle. Then if I invert that circle, the close point is that point inverted, which is now going to be the closest to my origin. And then I am taking 1, which is the edge. So I'm at this circle. I am subtracting that close point and dividing that by 2. So the difference between 1 and the close point would be the diameter of that inverted red circle divided by 2 to get the radius. And so there that is. Okay. And so I found that. And then I got its numerical value. And that's close to the ninth. Ninth would be 0.1111 repeating. And so we see it's close to 1/9, but it's a bit bigger than the 1/9, as my original picture did seem to suggest. Okay, and now I'm just putting the inverted red circles in there. And so this is my inverted honeycomb lattice. And then I have, here's what I just added. I found the position of the radii. So that would be the close point plus that radius we just found, or 1 minus that radius we just found, either way. But that was this 8 plus 2 times the square root of 3 divided by 13. That was the radius from the center to the center of these inverted red circles. And then so cosine and sine to get the x and the y of them. And then here is that radius of the inverted circle, which was close to a 1/9, but a little bit bigger. And that's the drawing. So there is the center circle, which was the circle of inversion. These blues are the inverted circles from that's these blue circles inverted. So they are the inscribed in the honeycomb, and then these little red circles, which were inscribed in little triangles, are these red circles here. But they correspond to what I wanted here, which was draw. I have 6 circles going around, and then what is this sort of interstitial radius? A little bit more than a 9. Okay, that's what I wanted to show in this one. Thanks for your attention.